In this video, we'll try to understand how to write down steady flow energy equation in case of various devices like steam condenser, then centrifugal compressor, throttling process, etc. So let us start with our steam condenser. Now we know that in case of the steam condenser, the cooling water is supplied from one end and that particular water will absorb the latent heat from the steam. So wet steam is coming from the steam turbine. So as you can see over here, from this side there will be entry of the wet steam from the steam turbine. Then it flows over the tubes through which the cooling water is flowing. Cooling water will absorb the latent heat from the wet steam and the wet steam will get converted to the saturated water and then it will be given to the hot well. From the hot well it is supplied as a feed water to the boiler. Now in this particular case, let us see how to write down the steady flow energy equation. Now as the heat is rejected from the system, Q is taken as negative over here. So applying the steady flow energy equation, there is no work done, so W will be equal to 0. Changes in kinetic energy and potential energy, they are negligible, so they are neglected, and the heat is rejected from the system, therefore it is considered as negative. So kinetic energy is 0, potential energy is 0, so it is only m into h1. Then heat is rejected, so instead of plus q it will be minus q over here. Then there is no work done, so this particular part will be 0. Kinetic energy and potential energy, they are negligible, so only mh2 will remain over here. Now transfer minus q on the other side and mh2 on this side, so q will be equal to mh1 minus mh2, so this is nothing but h1 minus h2. Now let us see the another application, that is the evaporator. So we are having the evaporator coil as you can see over here, and we have to write down the steady flow energy equation for this. The application that we are considering over here is the liquid refrigerant that is entering inside the evaporator coil and the vapor is going out. So the refrigerant liquid will absorb the heat from the substances which are placed inside the evaporator. Now for this, what will be the steady flow energy equation that we have to see. So let us write down the steady flow energy equation for this. There is no work done, so work done W will be equal to 0. Changes in kinetic energy and potential energy, they are negligible, so they are neglected. So we are left with only m into h1. Kinetic energy and potential energy, they are negligible, so they are neglected. Then m into h2, all the other parts they are 0. So kinetic energy, potential energy and W, they are 0. So we can say that Q will be equal to, now transfer this plus mh1 term on the other side, it will become minus mh1. So it is h2 minus h1. So here it will be h1. So this is the simple equation that we have obtained from the for the evaporator. Now let us see the another application. So another application is that of the centrifugal compressor, in which the air is compressed in the axial flow compressor as shown over here. So air will be entering inside the compressor over here at point 1 and then it will be compressed, and it is the compressed air is given out for the various purposes. Now this centrifugal compressor, it is driven by the electric motor, and the electric motor shaft and centrifugal compressor shaft, they are coupled by this coupling. So electric work is supplied, so W is supplied to the system. So as the work is supplied to the system, it is considered as negative, and the heat is rejected from the system, so that it will also be negative. So we can say that applying the steady flow energy equation over here, changes in potential energy, they are negligible. Then heat is rejected from the system, hence it is negative. Work is supplied to the system and hence it is negative. So we can say that in place of plus Q, now we are having minus Q. In place of W, we are having minus W. Then potential energy, that is mgz1 and mgz2, those are negligible, so those are 0. So we are left with only kinetic energy and enthalpy and heat over here. So we can say that this is the required equation for the centrifugal compressor, that is m into 1/2 C1 square plus H1 minus Q is equal to m into bracket 1/2 C2 square plus H2 minus W, where this first part is the kinetic energy, this is the enthalpy, this is the heat rejection, and here this is the work supplied to the system. Now let us consider our last application, that is throttling process. In this particular case we have considered the application of the capillary tube, which is used as an expansion device in case of the refrigeration system. This capillary tube is having very small internal diameter, so when the fluid is allowed to expand for a longer period of time or for longer length through a very small aperture, then the process is known as throttling process. And as the liquid or the fluid is allowed to pass through a very small aperture, due to friction, the frictional heat is generated and that gets added to the fluid itself, and the quality of the fluid will improve. For example, if you supply the liquid refrigerant, then you will get the vapor or wet vapor refrigerant at the outlet. And during this particular expansion process, the system is isolated, so there is no heat transfer, there is no work that is done over here, and changes in potential energy and kinetic energy are negligible. So if you want to write down the expression for this, then it becomes very simple, because kinetic energy part is 0, potential energy part is 0, then there is no heat interaction, so Q is 0 and W is also 0. So we can say that we are left with only mH1 on the left hand side and mH2 on the right hand side. M will get cancelled up, so we can say that specific enthalpy or enthalpy before throttling remains same as enthalpy after throttling. Only thing is that the quality of the working fluid will improve. For example, if it is a wet, then it will become superheated. If it is liquid, then it will become vapor or wet vapor, etc. So in this way we can write down the steady flow energy equation for the various devices. Thank you very much for watching.